What happens at the end of a star's life? Does it explode in a supernova, become a black hole, or just slowly get dimmer until it's no longer seen? This is a lesson on astronomy. So, astronomy is the science of objects and phenomena that originate outside of the Earth's atmosphere. So, one of the things stars and distant suns do is emit electromagnetic radiation, and then we can study them using telescopes. The closest star to Earth is the sun, and it has a high temperature and pressure that fuses nuclei together in a process called nuclear fusion. Now, nuclear fusion results in the release of a helium nucleus and gamma photons. Then the energy from the photon released in the nuclear fusion is absorbed and then re-emitted. The sun is also made up of visible light and infrared radiation at the surface, and it emits all types of EMR. The hottest parts, or the core, emit the highest energy EMR, so gamma rays. Solar flares are eruptions in the sun's atmosphere due to magnetic fields and emits mostly X rays and gamma rays. So the atmosphere filters all electromagnetic radiation except radio waves and the electromagnetic radiation close to the visible light spectrum. So gases that absorb the radiation are the ozone, which absorbs UV radiation. Water vapor, methane, and carbon dioxide absorb infrared radiation. The mesosphere and ionosphere absorb X-rays and gamma rays. And electrons absorb long wave radio waves. Now, light has a variety of different properties. One of them is the property of refraction, which is the bending of light as it moves into substances that have different densities. Another one is reflection, where light waves will bounce off at the surface. Polarization is the ability to force a wave to vibrate in only one direction. So you might have had polarized sunglasses that allow you to see more easily into a water surface. And then diffraction, which is the bending of a wave as it passes through an opening or an object. So when we look at these different examples, we have reflection where the light waves will hit an object and then bounce back. Refraction, where light bends as it goes into a surface substance that has a different density. So if that straw looks kind of bent in your glass or your feet look really big underwater. Polarization, which causes the waves to vibrate in only one plane. And diffraction, which bends light as it goes through a small opening. So one of the devices we use to explore outer space and study astronomy is telescopes. So the first telescope was invented about 400 years ago and studies electromagnetic radiation, primarily visible light. The first ones anyways. So there are three general types of telescopes. Refracting telescope with two lenses, reflecting telescope with lenses and mirrors, and then multi-wavelength telescopes. So the refracting telescopes were first developed by Galileo, which used two lenses, a concave lens and a convex lens. Now, some problems with older refracting telescopes is that the quality of glass was very low and that the opening was too small. The diffraction between these caused errors in distance to the source of the electromagnetic radiation. So they weren't the most effective at studying astronomy. Reflecting telescopes use a curved mirror that focuses light using reflection. So mirrors don't separate light into colors like lenses do, and therefore you have a higher resolution. Because you can have a larger opening, there's less diffraction that occurs, and mirrors can be supported from underneath to maintain their shape so that these telescopes can get even bigger. We can use reflecting telescopes to gather visible light, infrared radiation, as well as ultraviolet radiation. Multi-wavelength telescopes are advanced telescopes that are at high altitudes or orbit the Earth, and they can gather many different types of EMR. Sometimes we have radio telescopes, which are a huge dish because, again, the wavelengths are very large, and they produce lots of diffraction. So we mainly use these to collect data. Now we have X-ray telescopes like the Chandra X-ray telescope, which uses two mirrors and an X-ray, and this one orbits the Earth. So here we can see different types of telescope looking at different objects. So in that first the top left, we can see two images from the Chandra telescope. One is X-ray blue, one is X-ray green, the visible light from our Hubble telescope, and then the infrared light from a Spitzer telescope. And then they're all combined together to give us that multicolored image. Then moving over to the right, we have something, a vision of an X-ray telescope, and then another telescope of the same image. So when we combine these images of different EMR, we're able to get a more complete picture of the objects in outer space. When we look at starlight coming from distant objects, scientists are able to use prisms and diffraction, which is again the bending of light, diffraction grating. So we're able to separate the light into its different visible components to analyze the electromagnetic radiation into different wavelengths. So objects at 6,000 degrees Celsius emit mostly visible light, and it creates a rainbow or colors called the continuous spectrum. So this is all the shades from red to violet. So beyond the sun, the spectrum is not continuous, but it has dark lines where radiation has been absorbed. And this is called a dark line or absorption spectrum. So you'll see mostly color with some black spots in between. These spectrums can be used to determine what gases are in a star. So when a current is forced through a gas, the gas emits wavelengths. Emissions are a bright line spectrum. Now, these spectra would be analyzed using a spectroscope attached to a device that calculates wavelength. So in the top left, we have our emission spectrum, and this is the forcing of a current through a gas. So we're able to see exactly what lines would be emitted by different gases. And then we have a absorption line spectrum at the bottom, is where we have a cold gas, and then we force that light through a prism, and we're able to see what wavelengths of light were absorbed. So which gases had lights that were absorbed. Using this, we can identify the components of different stars by looking at a known sample, like in the top left, against an emission line spectrum in the bottom right. And we can compare, and then we can identify which gases are in different stars. So the Doppler shift is something we've all experienced when we've heard a vehicle getting closer to us and getting louder, and then getting quieter as it moves away. So as an object that's making a wave moves toward us, the frequency gets higher, and so we'll experience that as a brighter light or a louder noise. And then as it moves away, it has a lower frequency, so we'll experience this as a quieter noise or a dimmer light. Now the same happens with electromagnetic radiation, but we call it redshift and blue shift. So a blue shift, as we're moving towards a more violet color, is a higher frequency, and that object is moving towards us. A red shift, because it has a lower frequency of red visible light, is an object moving away from us. So when we see objects in outer space and we compare them to what their light spectrum was in previous years, if it's getting more blue, we say that object is blue shifting and moving towards Earth. Or if that body now emits more red wavelengths, we say it's red shifting and it's moving away from Earth. So stars are formed over millions of years. Space has gases and dust in it. And over time, the gravitational forces between the dust and gas result in a nebula, which is a large, highly compressed cloud. And as those gravitational forces continue, new stars are going to be born in a nebulae. The second phase of a star life cycle is called the main star sequence, and this is where our sun is now. So gravity creates heat and pressure to fuel those fission reactions. Larger stars typically have shorter lifespans because they have more pressure and therefore generate more heat, which leads to more rapid fusion reactions, so they run out of fuel quickly. So smaller stars will last longer. So when we look at the death of a star cycle, so they're going to run out of hydrogen, their main fuel. Then gravity is going to cause their core to collapse, which incidentally causes an expansion of the outer core because there's going to be more heat generated. That expansion then is going to lead to cooling, and the cooler, larger star is now known as a red giant. So in this image, this would be our sun as a red giant after its core had collapsed, and Earth would be completely engulfed, and the orbit of Mars would sometimes go into the red giant, and then sometimes it would be out. So that just gives you an idea of how large our sun will be once it expands into a red giant at the death of its life cycle. So after the large giant, a medium star, which is up to 1.5 times the sun, so our sun is a medium star, it will become a white dwarf, which is a stable star that has no fuel that radiates leftover heat. A huge size star, which is 1.5 to 3 times the size of our sun, have a massive explosion known as a supernova, which will blow away the outer layers of the star. And then a neutron star is going to emits radio waves, is going to be what's left over. And a giant star, once it collapses, will be a supernova that then results in a black hole. So an area that's so dense, gravity, and has such high gravity, even light cannot escape it. So when we look at the summary of a life cycle of a star, we have a nebula, which leads to our main star sequence, medium stars, and after they expand into red giants, a medium star will then become a white dwarf, a huge star will have a supernova explosion leading to a neutron star, and a giant star will have a supernova explosion leading to a black hole. I hope you enjoyed our lesson on astronomy.